Model, for example, an engineer would build a bridge, and they would build an actual model of the bridge. That's a physical model. Okay. Generally, the engineer may do a behavioral model of the bridge. Now, this is the Hill model, and this Hill model actually has been around for many, many, many years, and it's been used in muscle mechanics to try and understand voluntary human movements. And it has three components to it. The SEC is called the series elastic component. The CC is the actual contractile component. And the PEC is the parallel elastic. Structures within a muscle that represent any of these three. Okay? That's why it's a behavioral model. These three components can go together to give you the behavior of what the muscle does when it's stimulated, but they are not components in the model. You often hear people saying, oh, the SEC is, the series elastic is the elasticity of the tendon, okay? Or the PEC is the elasticity of the fascia surrounding the muscle. That's not true. It just is not true. And please, if you learn nothing else today, learn what a behavioral model is. It models the behavior of the muscle. So we're going to start off with the contractile component. And the contractile component is the active element that turns all of the signals of the nervous system into force. And the magnitude of the contractile component depends upon its mechanical characteristics. And these are explained in four separate relationships. These are the stimulation activation, or the SA, force activation, FA, force velocity, FV, and force length, FL. If you've taken any kind of anatomy or biomechanics, you'll probably be very familiar with force velocity and force length. Okay, so in stimulation activation, okay, this concerns how the nervous system is related to the muscle's intrinsic force application. And physiologically, this property reflects the excitation-contraction coupling process in which the alpha neuron potential trigger the motor action potentials traveling along the muscle. Okay. And the MUAPs, or the muscle unit active potentials, are carried inward through a structure in the muscle called the transverse tubule system and the sarcoplasmic reticulum, where they cause a release of calcium ions into the sarcomeres, initiating the movement of actin and myosin, and thus causing a muscle contraction. This excitation-contraction coupling is actually what we would call stimulation. And it's independent of the actual force production. Okay. So, this complex responds to the calcium that is released. And it changes it from a resting state where there's no cross-bridge attachment and no force potential into the activated state in which force production occurs. Other factors, which I'm not going to deal with, also affect the force production. Motor unit recruitment and rate coding. For modeling purposes, both stimulation and activation are placed on relative scales from 0 to 100%. We can't actually measure a value for this. We just say it's relatively somewhere between 0 to 100%. When a motor unit is initially activated, there's a short time delay between the onset of the neural action potential and the activation at the cross-bridge level. And basically, this is a result of transit time and the length of time for the calcium ions to be released. Okay, so this is a figure looking at the percent stimulation and the time over which the stimulation occurs. And what we have is two things here. The stimulation, and you can see the stimulation goes up, across, and down. And it's almost at 100%. It's like just a rectangle, okay? The activation, if you notice, goes up, and it sort of curves. So the peak stimulation and peak activation don't occur at the same time, as I just said. And of course, what happens when it comes down, there's no more activation, but there's still a level of contraction. And this deactivation takes time. And that's why you see this tail running off. And it's mainly to absorb the free calcium. Okay, now the term force potential was used to emphasize the fact that the activation is a state in which force can be produced, rather than an actual force level. Okay? All we're talking about here is the fact that force can be produced. The actual force level in newtons depends not only on the activation, but also the kinematic state of the contractile component. That is it longer, shorter, stays the same, whatever. And we need to convert the state of activation into an actual force level that is expressed either in newtons or as a percentage of the muscle's maximum force. To keep this force independent of any specific kinematic state, the force-activation relationship must be conceptual only. Okay, and this comes back to the fact that it's a model. And it is impossible to measure the force produced in the absence of the specific contractile component kinematic state. Okay. The force-activation relationship is direct and linear. Could you go back just 1 second? Next slide. The force activation is direct and linear. Now, this is a problem because the body doesn't work in a linear fashion. It always works in a nonlinear fashion. But we have to make, when we create a model, we have to make some assumptions. And one of these assumptions is that some of the things that we're talking about have to be modeled as linear. Okay? So 10, 20, or 50% activation represents 10, 20, or 50% of the force. And now we come to the second component, the force velocity. And the most important contractile component mechanical property is the effect of velocity on the force production. And it seems like there's an equation missing here, but we'll just leave that. This is the equation that was developed by A.V. Hill. And if you look down here, we have the different kinds of muscle, slow twitch muscle and fast twitch muscle. And you see force, and P naught represents the muscle at its resting length. Okay? And you can see that you have these hyperbolic curves going from, that represent the velocity. And of course, to the left of P naught would be the eccentric, the lengthening muscle, and to the right would be the concentric. And you can see that as you go faster in both slow and fast twitch, the force decreases. That's a characteristic. You often do this, or at least I used to do it when I taught undergraduate biomechanics, showing that if you move faster, you can't generate as much force in the muscle. Okay. Now, the dynamic constants are muscle and species specific and dictate the exact shape and rectangular hyperbola and its intercepts P naught and V max on the axes. You can't just take a force velocity curve from a particular animal, for example, and then apply it to a human, or vice versa. Predominantly slow twitch muscles have different dynamic constants than those of fast twitch muscles. I hope all of you are familiar with the difference between fast twitch and slow twitch muscles. The maximal shortening velocity, is in fast twitch is roughly 2.5 times faster than the slow twitch muscles. And I should have mentioned this at the beginning, but going back, the Hill equation refers only to isometric or concentric contractile component velocities. It really doesn't do very well with the eccentric mode. Although we've extended it to become like, we use it in trying to explain eccentric behavior, eccentric muscle behavior, that is. But it's really only for isometric and concentric. So the force length is basically is the dependence of the isometric force production on the contractile component length. And this figure shows you that when the muscle is at its resting length, 100%, that's when the maximum force is produced. So in terms of the biceps brachii, if you're in this position, okay, with the elbow flexed, that's when you're strongest. You're weakest as you go like in that direction and go in this direction. So these, I'm going to skip over a lot in the next few slides because these four properties can't be looked at individually. They have to be looked at because they interact. Okay, and in order to understand contractile component, you have to understand how they all interact. But the interactions are very, very, very technical and very sophisticated. When force output is required, the central nervous system initiates the process by sending a stimulation signal to the muscle. And the signal causes the activation of the contractile component according to these four relationships. Okay, and there. The CNS modifies the stimulation signal as needed to regulate this contractile component stimulation. Okay. Now this is it, trying to look at this in 3D, and this is why it's so complicated. The control of force is more complex, as I said, and when you look at it in 3D, you can see, for example, that I've put a green dot there. The green dot indicates for a particular contractile component length and velocity, which will dictate the force produced. And you can see it's about 65% produced for it to be at that point. And of course, as it changes, the interaction between length and velocity, then the amount of force produced will change. Now, the series elastic component, it tries to explain the elasticity of the muscle. Okay. If you took a muscle out of a cadaver and stretched it and let go, it would be like a rubber band going back. And as I want to repeat again, the series elastic component is not a physical structure within a muscle. It represents the behavior of physical structures. Okay, and here's the Hill model again. And any force the contractile component produces is exhibited across the SEC. And this is why it's very easy to suggest that the SEC is the tendon, because that's exactly what the tendon would do. And one obvious contributor to the SEC velocity is that the tendon that joins the muscle fibers to the skeleton. And, but there are other things, including aponeurosis or an inner tendon, which connects the external skeleton to the muscle fibers and connective elements to the muscle fibers. Now, the series elastic component is a behavioral model. Again, I can't overemphasize that. And there's no exact correspondence with anatomical structures. And I've said that several times already. Okay. The SEC series elastic behavior is described by the force extension relationship. And you can see here that P naught is the resting force, that as the muscle is stretched, and you can calculate the stiffness of the muscle, K, and the stiffness of the muscle here is the change, the delta force over the delta length. And again, this is a nonlinear relationship. And it's an extremely important feature of the Hill model, and one of the parts of important, powerful influence on the muscle force response. Some experiments indicate that SEC is lightly damped. Now, damping just means that it works like a shock absorber. It's not completely elastic, but it will have a nonlinear response to it. And the damping characteristic unfortunately has a relatively small effect on the overall model behavior. Now, the parallel elastic component, muscles display this behavior even if the contractile component is inactive. As I said, if you take a muscle out of a cadaver and stretch it and let go, it will go back to its resting length. If an external force is applied across an inactive muscle, it resists but stretches to a longer length. And the resistance is not a response of the SEC because no force is being applied by the inactive contractile component. And the parallelistic component, and again, this is wrong. I'm saying people think that the parallelistic component is the fascia, but that's not true. Remember, behavioral model. And of course, this force-length relationship of the parallelistic component is highly, highly, highly nonlinear. Okay. So what we can see here is muscle force along the vertical axis and muscle length along the horizontal axis. And if you look at the black line here, okay, that would be just the muscle activation itself, the muscle force production itself. If you look here, this is the parallel elastic component. And if you look at the top, this is when you combine all of the forces produced by these individual components together. And you can see that the peak is greater when you combine the active and passive components with the together over just the passive by itself or just the active by itself. Okay. And like I said, this is why, for example, when you're going to lift a barbell, sometimes you see people doing this. They're just stretching all of the elastic components and then adding that to the contractile component. Now, okay, just a little bit of background on this. The Hill muscle model was actually done on frog's muscle. Okay, and the way it was done, the way Hill did it, was he used a bath like this, and it's called a rigor solution. He took the muscle, and what he did was he had a force transducer on the right-hand side and some kind of length measurement system on the left-hand side. And then he stimulated the muscle. And so then the muscle would lengthen or shorten. Well, actually short. So this provided a very nice model of muscle, very nice behavior of the muscle. And this is what it looked like. So we consider two responses, what we call an isometric tetanus and an isometric twitch. Now, this is the stimulation. The twitch is just a single stimulation. So it goes up and down quickly. The tetanus is a stimulation, but it's a continuous stimulation. So it reaches basically a higher level than just the twitch does. And so the tetanus differentiates and has a frequency of stimulation pulses that determine the force response. Okay, active force production. In response to the brief maximal impulse of a stimulation, the muscle force exhibits a relatively slow rise to its submaximal peak. That's the twitch. And the stimulation pulse may last only a few milliseconds, but the time to maximum peak twitch is from 25 to 50 milliseconds. So you see there's a delay. Okay. Now, at the beginning, before the arrival of the stimulation, the contractile component is inactive and produces no force. The SEC is unloaded in A. So no force, no time. The stimulation pulse causes the contractile component to be active and begin to produce force, according to the four characteristics that I talked about. And this force is expressed across the SEC, the series elastic component, which responds by extending according to the force-length relationship. Okay. I'm going to skip this slide altogether. And as the activation rises, you see there's a shortening which produces a force, and the stimulation, you see, goes up, and this is a twitch. So it goes up, and then it will decay. And consequently, the contractile component must be shortening by a relative amount, because the total muscle length, that is the contractile component length and the series elastic component length, is being held constant. That is, it's isometric. And after the peak twitch force, what you get is everything reversing, because there is no more stimulus, and so the force decreases, and you get a shortening of the muscle. And only at the peak where the change in force over time are the SEC and contractile component instantaneously in an isometric state, neither lengthening or shortening. But note that the SEC does not directly influence the amount of force produced. Now, there's a concept that is referred to as, it's called the active state. And Hill found that it was possible to delineate the effects of calcium dynamics from those of contractile component kinematics by describing the time force of the active state through the isometric twitch. And he defined the active state as the instantaneous force capability of the contractile component if it is neither shortening nor lengthening. Basically, if it's in an isometric state. While in the isometric concentric state, or the isometric contractile component state, the level of activation and the instantaneous length influence the force level attained. So what you have is, this is again the stimulation twitch, and this is the force production that you get. and comparing the time course of the active state with that of the isometric twitch force, it's clear that the contractile component is isometric if it is indeed capable of producing large forces shortly after the onset of stimulation. Go on. And the keys to understanding the shape of the twitch force profile are the sequence of contractile component SEC dynamics, the contractile component force-velocity relationship, and the SEC force-length relationship. Okay, go on. So you get something that looks like this. In tetanus, remember this is where there's a series of pulses. The active state goes up, and it'll stay there as long as it is being stimulated. In the twitch force, it goes up, the stimulation goes up and then comes down very quickly, and the twitch force does also. I think I'm going to skip this part. Okay. Can we take about a 5-minute break, please? I'm not. Can we start? Okay. Can you fix the screen? Okay. Everything that I've said up to this point, you know, I'm talking about a single muscle. And you can use a Hill model for a single muscle, an intact muscle. But, you know, sometimes musculoskeletal models obviously do represent any kind of human movement other than maybe a single joint movement. You need multiple muscles to do that. And it's really hard to look at individual muscles, muscle forces directly in humans, but you can through a muscle model. And muscle models can be used to represent the function of specific muscles. So what researchers have done is have created musculoskeletal systems with multiple muscles and use multiple Hill-type models with each one of the muscles. And the thing is, what you have to do then is you have to have functional characteristics of specific muscles to use as parameters in the Hill model. Hill models. We have a model that contains 62 muscles, and we have 62 muscle models, Hill models, to try and represent those individual muscles. So there's a lot of things that you have to know about muscle architecture, and I'm sure if you've taken any kind of anatomy, you probably are aware of these. One is pinnation angle, physiological cross-sectional area, fiber length, fiber composition, which I've already addressed, tendon length, and tendon elasticity. These architectural elements, these are, go back one, please. These architectural elements are important because they affect the mechanical properties of the Hill model, contractile component, and series elastic component. Okay? Oh, pinnation angle. This is generally with pennate muscles. So essentially what you have is the muscle fibers are off in, on an angle to the central tendon. And as the tendon, so you have an initial angle. As the tendon shortens, the angle changes. And that's important to know. In some simulations, though, the fibers rotate as well, and the pinnation angle actually increases as the fiber force increases. So we have some problems with that. Now, cross-sectional area, there's two states that you have to know about in sarcomeres. One is the sarcomeres can be in series or they could be in parallel. Okay? If they're in series, this is like a train. Every car representing a sarcomere, the cars in the train are all in series. Okay? In parallel means that it would be as if you could have 2 trains running side by side or 3 trains running side by side. Those sarcomeres would be in parallel. Now, if they're in series, each sarcomere may produce, let's say, 1 Newton of force. 100 sarcomeres in series would produce a total of 1 Newton. Okay? If they're in parallel, each fiber transmits their own force. So the more sarcomeres in parallel, the greater the force produced. So the same 100 sarcomeres arranged in parallel would produce 100 newtons of force. And if you think about it, just think about the muscles in the body. The muscles that are pinnate muscles generally are much stronger muscles than the fusiform muscles. The fusiform muscles are basically parallel fiber muscles. And a muscle's cross-sectional area indicates the number of fibers in parallel. And it's used as an indicator of the muscle's maximum force capacity. And to account for the pinnation angle, we use what we call the physiological cross-sectional area, which is the muscle volume divided by the fiber length. Okay? If you've done any kind of strength testing, I'm sure you're familiar with the physiological cross-sectional area. Now, fiber composition, I've already talked about slow twitch and fast twitch fibers. And this is all we have to talk about in terms of muscle mechanics. The distinction between fatigable and fatigue-resistant fast twitch fibers, though, you know, I'm not going to even talk about those, and we don't normally talk about those in terms of muscle mechanics. The basic importance in the slow twitch and fast twitch dichotomy arises from the separate activation time states and constants, which we already looked at, and the force velocity characteristics, which we've already looked at. The time for the force to rise during an isometric tetanus is longer for a slow twitch than a fast twitch muscle. So, the fiber tendon morphological characteristic. Each muscle tendon unit in the human body is unique. Okay. In the relative length of the muscle fibers compared with the tendon. You know, some muscles have enormously long tendon and very short fibers, and some are the opposite. The number of sarcomeres in series determines the length of the fibers. Because each sarcomere can shorten across its range by about 2.2 microns, the total number of sarcomeres in series dictates the maximal excursion that a muscle can undergo. The fiber length also determines the absolute fiber velocity during a movement. And the length of the tendon is important for similar reasons, because of the amount it will extend as the force is applied across its length. You know, some tendons are short and thick, and others are long and slender. They will determine the overall tendon elasticity. For example, more distal extensor muscles of the lower extremity often have long compliant tendons in series with relatively short fibers. You know, think about the Achilles tendon in that case. Or the tendon of the anterior tibialis muscle. Very long tendon, thin tendon. For a given joint muscle tendon excursion, the fibers undergo less overall excursion if the tendon was shorter and stiffer. And this means that fibers can operate at lower contractile velocities and therefore produce a given required force at a lower activation level than at a higher velocity. It seems like the construction of the human body took place with someone who knew what they were doing. And here, we look at the required force that the higher contractile velocity would require if the muscle were activated at 100%, okay, to attain the needed force. However, for a slower velocity, V2, the needed force could be generated substantial activation of about 30%. So these tendon properties really have a great effect. Now, this is the problem when you're using a model. You have to estimate some morphological characteristics which ultimately affect things drastically in the model, in the use of the model. The Hill model, you have all of these properties for a specific human muscles, and they're generally not available to us, especially if you're doing a model that has many muscles involved, and each one has its own Hill model, and each one has its own characteristics. And what we often do in these is we say modeling studies report the properties for an individual muscle actuator, usually estimated from muscle morphological and architectural considerations. You don't know these exactly, but you can have a ballpark idea. And, you know, there are some things that you can do direct joint measurements. For muscle groups crossing specific joints, you can generate values from what's a torque angle value or a torque angular velocity value. You know, sometimes you would use a biodex to do this, for example. So you also have analytical techniques. And analytical techniques, you know, basically you can think of mathematical techniques. One method is to use estimate specific model parameters and extrapolate from those information from animal studies. You know, muscle is muscle. Mammalian muscle is the same regardless. In fact, you know, all muscle is the same, has the same characteristics, maybe not the same sizes and such. You know, you can estimate force length characteristics by considering the number of sarcomeres in series. Another method is for force length is to extend animal results based on what we call the index of architecture of a muscle, which is defined by the ratio of fiber length to muscle belly length. In general, the pinnation angle dictates the length of muscle fibers relative to the muscle belly length. Another way people have done this, and I've done this in many instances, this is actually taken from a study that we did, is using imaging techniques, particularly MRI. And, you know, for the pinnation angle, for example, people have used ultrasound and gotten very good results. This is a cross-section of the leg of a human, and you can see DF. You all know what muscle that is? GA is the gastroc, soleus, GA. Okay, medial and lateral gastroc. The blob at the top there, that's the tibia. And the smaller blob, as you come down from that, is the fibula. And you can get a lot of information from these images. One of the things that you can do is these are the moment arms, and we know the angles of pull, so we can calculate the torque about the different joints. Okay. At the top, these are images from ultrasound. And so if you look at, in the left-hand one, the gastroc is at rest, and this is the lateral head, and then below that is the posterior solus, and you basically mark beads on the tendon, and then what you do is an MVC and see how much those beads move, and that will tell you or give you an idea of the muscle force being produced. The bottom of this actually is graphed out. So, you know, you can see the force is extended as the torque increases. And we also have computational techniques, a little bit more complicated. Not all muscle parameters can be assessed with direct measurement techniques. And one way to overcome this is use what we call an optimization approach. And the optimization approach, we use experimental techniques to define joint relationships for a particular subject, and then use a musculoskeletal model to replicate these relationships. And using computational optimization algorithms to find the set of muscle parameters that fit the experimental and musculoskeletal model data. Okay. And you can augment this with some, you know, with some imaging techniques as well. Now, you know, so far all I've talked about is one model, but there are several other models. And Graham in the chapter calls this beyond the Hill model. But the Hill model, I would, you know, is by far the most used model. It's the most prevalent. There are shortcomings of the Hill model, and partly due to its scope, and it's meant to describe behavior of whole muscle or single fibers under physiological contractile lengths and speeds. So you can't go to any kind of extreme. Okay? So there are 3D structural models. And this is mostly, you know, I've never done this, and I don't really know anyone in my immediate field who uses it, but they're called lump parameter models. And they use very, very simple geometry, and they determine muscle lines of action, length, and moment arm changes when used to represent specific muscles. And the muscles represent the muscle line of action by a series of straight line segments that join the origin and insertion of the muscle. And these models are not without their weaknesses in the fact that all fibers undergo the same length changes and have the same moment arm, which is not necessarily true. More detailed information geometry might enhance our understanding and lead to more accurate force and torque production. You know, I mean, if you have more information, obviously you're going to have better results. These are 3D structural models. This is by Scott Delp, and it's the hip flexion angle. And you can see the model value of the iliacus. And Arnold, these are the psoas fibers. And over here is basically a figure of how these models are formulated. You can see they just draw straight lines with all of the fibers. Another way of using this is using what's called a finite element analysis, or FEA model. And this is just a mathematical technique based on partial differential equations, which I'm sure you're all familiar with. The FEA approach is represented as a very, very large number of smaller elements. So if you have many, many, many fibers, you would probably go to an FEA approach. Now, this is another type of models, the linear engineering models. And these are called Rheological Models. And they have relatively simple properties and with more complex and mechanical characteristics. The most common one used is called the Hookian model, you know, a mass spring model. And this is a purely elastic body whose properties are completely described by the stiffness of the spring. And another is called the Newtonian body, which is essentially a Hookian model with a damper. The damper gives it a nonlinear characteristics. I've done the model over there. On the left is a spring, and you can see K completely describes the force displacement relationship. And over here, in the dash pot is usually configured like that, and it is completely configured with by a value beta, which is the force over the velocity. Okay. And you can combine these together. This is one that mimics the Hill model. It's an engineering model, has a contractile component and an elastic component, a series elastic component, and it has a dash pot to give it the nonlinear approach. The advantage of this, as you can see, it has a reduced computational cost. It doesn't take very long to compute the values for it. And of course, you can see the disadvantages are only isometric and only fully activated situations. Nothing in between. And no concentric, or eccentric rather. This is the most famous model, the Huxley model. And this model basically is more widely known as the sliding filament model, where he describes the sliding of the actin and myosin fibers that end up producing the muscle force. And one of the strengths of the model is to produce both mechanical and metabolic characteristics of the muscle. And the model assumes that the cross bridges act as independent force generators. You know, so each interaction between actin and myosin, the myosin head, is considered a force actuator. And I'm not going to go through this. You could read this when you get the PDF. And the model assumes that the muscle is maximally activated and that there is no elasticity. Again, these are assumptions that you have to make. This is something that is getting more prevalent, are metabolic cost models. The Huxley model is not suitable in dynamic situations or when you have series elasticity to be considered. There are several examples of models that use to predict metabolic energy cost of muscle contraction. One of my former colleagues at UMass, Brian Umberger, did a lot of work in this area. Such models are useful in estimating mechanical and metabolic expenditure during whole body movements that can be studied with musculoskeletal models. And actually, I will show you an example of this in the computer simulation talk. So I'm finished my talk. I've gone over everything I know about muscle mechanics, which is not, I wouldn't say at the expert level. Graham, you should have asked Graham to give this talk, and rather than me. But if there are any questions, we can do questions now. Not reliable at all. I know many people have tried to, come up with ways of relating peak activation of the EMG with, the force production and force output, and it's very dismal relationship. Many people like. I've asked experts on this, and I remember several years ago I asked Carlo De Luca, who wrote the book Muscles Alive, about this, and he kept saying, "Don't ask that question." I mean, they're obviously related, but they're not directly related, and of course, no one knows how directly they're related. You can't give it a coefficient and say this is, if you multiply the signal by this, you'll get this. I don't know of anyone who even considers that a viable area of study now. And of course, Carlo's dead, so he can't do it anymore. But I don't know. I know I'm very, well, personally, I'm very, very suspect about EMG anyway. I only use it as off-on, and I know many people use peak activation or area under the curve and that, but it still doesn't correlate very well with the actual force output. Yeah. Yeah. Mm-hmm. Mm-hmm. In terms of force production, I don't think you can. I think you get information from the EMG that is worthwhile. Like the peak activation of the EMG is important because that tells you that's when the neural response is at its greatest influence on the muscle. Okay, but that doesn't directly compare to force production. To me, I think it's very, very important for BMG that you can look at on and off. And like I said, in my career, I've always avoided doing anything with EMG more than on-off. Oh, I guess I'm using co-contraction. The fact that they're contracted or not. But that again is just on-off. So, sorry I can't answer your question. Actually, one of my colleagues, who's an author on the book, Gary Kamen, first started doing that when he was working with Carlo De Luca. And, you know, he used fine wire electrodes. You know, the best I thought that they could get out of that was the recruitment pattern of the different muscle motor unit action potentials. Or not the, yeah, the action potentials.
So, just like you said, it's a model.
Mm-hmm.
Okay? But then, and we were talking during lunch, that one of the problems of the model is to accomplish about the movement variability. And what do you think that between all the, because all those models, they mimic part of the body, behavior, physiology, energy.
Mm-hmm.
And do you think that, for example, if we try to combine models or try to individualize the information about the body, will give us a look into the movement variability, or this is not the pattern?
Well, the reason why movement variability occurs is the redundancy of muscle function. You know, there's not one muscle that does one action. There may be several muscles that do the same action. And to me, the variability, the movement variability can arise when you use different muscles at different times. You know, in other words, you've got these multiple degrees of freedom, and you know, you don't have to use all of them at once. And very rarely do you ever use all of the muscles that perform a specific action at one time. So, and you know, again, it's hard to you know, put that into a mathematical statement. And this is why people have had such a tough time with movement variability and muscle models. You know, the model is a model. It will give you out the mathematical response. And if you put the same information in, you're going to get the same information out. Okay? And like I said, I know people who are now trying to model variability or include variability in their models. And it has turned out to be a very difficult task. And I guess, you know, it's the problem of the redundancy. Well, that's not a problem. That's a good thing. I shouldn't phrase it as a problem. The redundancy is a good thing, and the variability turns out to be, I think, is a good thing too.
But I say that, we can say that, for example, the variability, how to include variability into our biomechanical models is a physical problem, means that we don't know exactly how to do with having the same mechanics and have the same equations, but having different kinematics, or we don't have the right mathematics in order to give us the same input and have two different outputs.
I think it's everything that you just said. You know, so far we've resisted using nonlinear mathematics. You also have the problem that even though that you have many muscles doing the same action, they all have different characteristics. And that's hard to, you know, put into a model.
But then you mean non-linear, very complex, or still non-linear and simple model? Because the idea of model is always to make something more simpler than that.
Yeah. Nonlinear is much more complex. You know, you're right that you try to simplify your model as much as you possibly can. But the problem is the simplification comes at a cost. You know, is the answer you get the correct answer? You know, I have no idea how, well, maybe what you'd have to do is with every iteration that you do is randomly assign some parameters that will change randomly in each individual muscle and see how that works out. But that's not easy. And of course, it may not work out, and it may give you junk. All I know is it's beyond my capabilities.
Pessoal, alguém quer fazer uma pergunta? Vocês podem abrir o microfone e falar em português. A gente traduz o jogo. Tá? Então, aí podem abrir o microfone e falar. Franklin, quer falar alguma coisa aí? Você trabalha com modelos?
Thank you, Professor Hamill, appreciate your open and ever opportunity to speak here. The question about model, considering the multi-body system, the problem for optimize, how do you do first step so connect it in your place, considering two joins to model and start optimize the situations.
If I, yeah, I think I do. If I was starting off to develop a muscle model, I would start with one muscle and maybe crossing one joint. And then from that, you would have to, once you've got that and you're confident that works, then start expanding to maybe multiple muscles that cross the same joint. And that would give you the amount of force that would be necessary to move the joint. You'd have to combine the thing into a musculoskeletal model, which you've got the muscle models, but also a mechanical model. But, you know, if you're going to do this yourself, you know, and if you're interested, if you look at the book, or if you have the book, in the chapter 9, Graham actually had a whole section on, you know, how to do a muscle model. And I did not report on that today, but, you know, he gives you the steps that you need to take, you know, for one muscle. Of course, if you're doing multiple muscles, you just repeat that with the individual muscle characteristics.
E aí, pessoal, o Franklin inaugurou. Vamos ver se vocês têm mais coragem de perguntar.
No more? Okay. Actually, well, if we're ending, one of the things that I learned a long time ago from a physics professor, actually, who did modeling. He modeled binary stars. But there was a quote that he used to state, and it was made by John Box, another physicist, and I think it was from 1967. And the quote was, "All models are bad. Some are useful." So keep that in mind.
Okay, Joe, if we don't have any more questions, then we can finish for today. Thank you, Joe. Obrigado, pessoal. E amanhã vai falar sobre modelos computacionais. Tá? Então, obrigado.
Oh, there's a lot.
comparing to other fields of biomechanics?
I think it's the sexy discipline of biomechanics. I think modeling and musculoskeletal modeling and muscle modeling, that's where everything is going.